Hello, my dear students, and welcome to our video help session for exercise 3.2. I want to walk you through a couple of examples, even give you the answers, and work through them. Remember, you have to show your work to get credit, to get full credit. If you don't show your work, even with the right answer, I won't give you credit for the problems. And if you show your work and you don't get the right answer, then I can find your mistake if you show your work and propagate your error and give you partial credit. So try to remember to do that. So if you go and download the assignment, you'll see that it asks you to develop a basic skill in determining the formula mass. And we do this by using the atomic masses for the atoms and the molecules. So let me go ahead and work the first one. The first one calls for what is the formula and the formula mass in grams per mole for each species below. And A is ammonium sulfate, very common laboratory chemical. We use quite a bit. It's used especially in biochemistry because it's used to precipitate proteins and concentrate them. It's a very gentle way to precipitate and concentrate proteins because as you add it to solution, proteins precipitate out because there's no room left in solution for them. The ammonium sulfate takes up all the room. That's a simplified way of looking at it. But its charges in the ammonium sulfate tie up all the water in its ability to hydrogen bond, and now it can no longer bond to the protein. So we're in our lab. I'm apologizing right now for forgetting to go pick up some whiteboard erasing fluid so I can get a clearer, cleaner background on our whiteboard to work this first problem. And I want to show you the steps, and I'll work a couple of them for you, give you the answers, and work through them. So this has two parts. One is naming or taking the name of the compound and giving me the formula. That's an important skill, as important as some of the skills you have in the other assignments, in the previous assignments, in the Module 1 and Module 2, where you were given the formula and asked for the name. So this has the polyatomic ion, ammonium. You can get that information. Look, these assignments are what? Open book, online. You have your book in front of you, you have your notes in front of you, you have Google in front of you. So I will post a copy of this, and go ahead and track me as I go along. This is a smaller version, I will scan it and put it in, of the Flynn Scientific chart of the charges, names, and formulas of common ions. And if you look, the first one on the list is ammonium, NH4+. And this compound is ammonium sulfate. So if I go to find sulfate, it's way down here, it's SO4 2-. When I put those together to make a compound, I need a neutral compound. So my 2- have to be balanced by 2+, and this ammonium ion only has 2. So let's go and write the common formula for ammonium sulfate. And let me use something other than red that shows up better on our recording. Ammonium sulfate. Ammonium, that's my polyatomic ion, cation, sulfate. In America. It would be a pH in Europe and England and much of the world. This is NH4 plus, and sulfate is SO4 and 2 minus. So that's my formula for ammonium sulfate. So the way we get our formula mass is just to take our atomic masses and add them together. So when you look at a periodic table, there's a big red number on it. And we call this the what? Atomic mass. Technically, average atomic mass, and we covered that in the last unit. And this, you may have in high school emphasized atomic mass units. When I took chemistry, we called them Daltons. Depending on whether you're a chemist or a physicist, those are defined as 1/12 of a carbon-12 atom or 1/16 of an oxygen-16 atom. But we don't really need to work in atomic mass units because we don't work with individual atoms or even individual molecules. They're so tiny, and the actual mass in grams is, so minuscule, incredibly small numbers that we don't practically use them. But the beauty of it is, thanks to Avogadro and his work with gases and reactions of gases, that this value now stands for the average atomic mass in grams per mole. The mole being the unit that's practical. For example, a mole of water is about 18 milliliters. A big swallow, maybe about that much in a test tube. And a mole of ammonium sulfate, we want that answer in grams per mole, would weigh how much? So I need to add all of these up. So I need nitrogen, just going left to right, but I have 2 of them. And if I look over there on my board, my nitrogen, its atomic mass is 14.0067 grams per mole. Now your mileage may vary. If I look on this periodic table, my nitrogen is 14.00674. When I'm working my key and preparing my notes to talk to you now, I may use a periodic table that I keep in my notebook, or I prefer to use the Flynn Scientific Periodic Table of the Elements, which gets revised every year with the most current atomic masses. When I go to the periodic table, in my classroom here in the laboratory, I know that one's at least 8 years old because it doesn't have the atomic masses for the completed elements in the periodic table. So, but if there is a variance, it's way out in the 3rd, 4th, or 5th place. Now, 2 of them would weigh, so get out your calculator. Remember, you write the formula of your compound, and then you start adding up the individual atomic masses. I have 2 nitrogen atoms in this compound. They weigh 14.067 grams per mole each, and 2 of them would weigh 28.0134 grams per mole. So 2 nitrogens times that. This is all in grams per mole. You can use units, but since I asked for the value in these units, actually stating it is optional in this case, we have 4 hydrogens in each ammonium, but we have 2 ammoniums, so we have 8 hydrogens times 1.00795. We usually don't work with this level of precision when we're measuring things out in the lab, but that would be equal to 8.0636. And continuing on, we have 1 sulfur and that is equal to 32.066 grams per mole. And we have four oxygens. And each of those oxygen weighs about 16 grams. If you look in the periodic table, it's 15.9994, but out to 4 or 5 places, it's basically 16. And that is 63.9976, if you want to be totally precise, with the level of precision that we now have for these elements in the periodic table. And if you sum this up, this is equal to 132.1406 grams per mole. And by the way, that is your answer. So when I ask you, give me the formula, here's one answer, and here's another. And I just happen to have some ammonium sulfate here. It's also a wonderful fertilizer because sometimes you need sulfur. I'm not going to open this bottle, but if I look at this answer and our answer, there's usually a lot of data on a label in the laboratory. Less on these because they come from Flynn Scientific. They're more for teaching than they are for research, but it's certainly accurate enough for our purposes here in the, at least the freshman chemistry lab. But if you see this ammonium sulfate, I don't know if we can zoom in on it, but it gives you the formula, NH4,2SO4, and some other values like reagent grade, magnesium sulfate. I have another bottle, but it's harder to read. It's ACS, certified reagent grade, which is American Chemical Society. And it says the formula weight because technically with ionic compounds, we use a formula weight, 132.15. We said 132.14. Not bad. And when you do your problems, don't worry about those decimal places way far out, 4th and 5th place. They're not significant from a laboratory standpoint, at least in a freshman chemistry lab. And they will vary depending on your reference source, its age, and even its source and who they're quoting. So let's move on. Let's do sodium cyanide. I don't have any sodium cyanide, but I have potassium cyanide. It smells like almonds. We would never open this and stick our nose in it, since, as you know, cyanides are very toxic. In fact, now that I've touched this bottle, I'm not even going to scratch or do anything until I get a chance to wash my hands. But a very common reagent in the laboratory, especially handy in plating and electrochemistry experiments. So let me get us a little more room here. And move over. I apologize if my board is not real visible, only because I have the lights off over it so that when I do project on the board, it's more visible. So sodium cyanide. So if you go to your chart of the common elements, you look it up or whatever, sodium, of course, is Na for the Greek natrium, Latin name. And cyanide, it's an ionic compound of sodium ions and a polyatomic cyanide ion, -1. So sodium cyanide is NaCN, fairly simple compound. Very bad for your hemoglobin and oxygen carrying capacity, extremely toxic. So sodium is equal to 22.9898. according to the periodic table I used. Like I say, I'm looking up here, and it's 22.989707. And we don't have to multiply it by anything because there's only one of them. Carbon is 12. Actually, it's 12.0108. Again, depending on your chart out there. And nitrogen is 14. 14.0067. So, when I sum those, I get a formula mass of 49.0079 grams per mole. And this is your answer. This is the structure, the formula for sodium cyanide, and this is the formula mass for cyanide. So let's do one more, and I'll let you finish the last two or three. The next compound is another sulfate compound, this time magnesium sulfate. I've got a bottle of it right here. You may also know it as Epsom salts. You can buy this at Walmart. This is chemical grade. And this is a hydrate. Now this one is a heptahydrate. I didn't ask you for the structure of the heptahydrate. So this has, as part of its formula weight, 7 waters included, which are 18 grams per mole each. Oxygen 16, hydrogen's 1. There's 2 hydrogens in water, 1 oxygen, 18. So let's talk about magnesium sulfate. Sulfate is -2. Magnesium is a group 2 metal. It's always +2. You know, because I wrote a +2 at the top. But anyway, this magnesium has a formula mass here, but I'm not going to use that one. I'm going to use the one I looked up earlier. It's MgSO4. Magnesium is a +2 cation, group 2 alkaline earth metal, and sulfate is a polyatomic ion with a -2. So they combine in a 1-to-1 ratio. Remember, the polyatomic ions, those atoms stay together as a group, and it's treated as a single entity and named as such. So magnesium is equal to 24.3051 grams per mole. And then sulfur, which we had over there, is 32.066 grams per mole. And our oxygen times 4, oxygen is 16 in practical terms, but 15.99, how many did I do? 3,9994. And 4 of those would be 4 times that is equal to, as before, 63.9976. And when you sum this, our formula weight for this compound is 120.3687 for our anhydrous magnesium sulfate. So there's your first 3. You can go on and do the next 3. What I want to do is talk about the second problem, and given that we know the masses of the individual atoms and the individual components, we can determine how much is there. For example, I don't see the bottle I had out early, but I have a bottle of silver nitrate. And people always ask me, is there really silver in there? And of course there is. And the question is, well, here's a solution of silver nitrate with some copper in it, where we've replaced the silver nitrate in solution, we'll talk about reactions in the next module, with copper. And so the copper's gone into solution, and I have crystals of silver precipitating out in there, plating out, or reducing out in there. and it's a redox, oxidation reduction reaction. But I can recover that silver now, whereas it was silver ions in solution. And how much silver is there, and how much is it worth? And why does a little bottle of silver nitrate cost $100? It's because it's about half silver. And silver's been going up lately. So, one of the things we always want to know is how much, or, beginners at least always want to know how much is it worth. And so let's talk about that and practice finding percent composition. The ammonium sulfate's a great fertilizer. What we want to know, and what you would find if you bought ammonium sulfate fertilizer at Walmart, not the laboratory brand here, it would have percent nitrogen on it, because nitrogen is a component that's, the main thing you add to soils to help plants grow. Sulfur, phosphorus, and even other things as well. But, nitrogen is your limiting factor, even though the Earth's atmosphere is, 79% nitrogen. The problem is nitrogen gas is not usable by plants. You need to turn it into nitrate, nitrite, or ammonium. And it's very expensive. And it's expensive because it requires high temperature and high pressure. And those kind of energy costs are very great. But you can get nitrogen from the atmosphere and turn it into a usable form, but it's very expensive. It's a process called the Haber process. We'll talk about it later in the course. So let's talk about the first two of these in number 2. One of them is antimony bromide. Oh my gosh, SBBr3. It doesn't ask you to name it. And I guess you could call it antimony tribromide. I don't, have any of that. It's not rare, but it's not common because it's just not commonly used. And what it asks is, calculate the percent composition for the element shown in bold. So in this particular one, and highlighted, the bromine is emboldened. And let me stop here and say, depending on the semester, depending on the class, depending on whether or not we're teaching here at Sierra College in Pine Bluff or Phillips Community College in DeWitt or in Helena or Stuttgart, depending on where we're at, or other colleges and others that I act as an adjunct for, depending on where you are, depending on what semester, and even within a single class, there will be differences. You might have a different compound. You might have aluminum bromide. You might be asked to calculate the percentage of antimony, not the percentage of bromine. The process is the same. The journey, not the arrival, matters. If you are lucky enough to have antimony tribromide or antimony bromide, and it asks you the percent bromide, we're going to calculate that right now. And then in my head, I'll just calculate real fast the amount of antimony. If you have aluminum bromide or iron 3 bromide or something like that, you're on your own. But follow this path. So antimony, SB, has a molar mass, atomic mass, average atomic mass. For old people like me, I'll say average atomic weight. We know it's a mass. We know weight is a force. But it's the way we learned it. We weren't so picky about being quite so precise, but we were more precise in other ways. 0.960 grams per mole. And there's one of them. So that's all I need, 121.960 grams per mole. And the bromine, if I look at bromine, interestingly enough, bromine is one of two liquids in the periodic table. If you look at our periodic table, you'll see two elements of different color. On this one, it's blue. And of course, you know, mercury, a liquid metal, and bromine, a liquid halogen, is present as Br2. And you may not realize this, but at one time, Arkansas was the world's leader in production of bromine. More than other countries, other people, other anything. I think we're number 3 now. But a third or more of the world's supply of bromine comes from a little place in South Arkansas near El Dorado, where the remains of an ancient ocean concentrated and turned to brine. Now you get bromine out of regular seawater, but it's much more concentrated there. It's the same, part of the same geological structure that now we're finding lots of lithium in. But in a little town called Smackover, you know, it's sitting right on top of this brine, deep underground, remnants of an ancient ocean that has high concentrations of bromine. Right now I'm coming to you from CR College in the chemistry lab here. It's a very nice, well-equipped chemistry lab. And just over here are railroad tracks, and it scares the hell out of me watching those railroad cars come by from Smackover going up north to the factories where bromine is used to make plastics and pharmaceuticals and other things, that these giant tank cars of bromine, I just hope nothing happens. It's not as toxic as chlorine though. And if I hear of a tank car rolling over, just run. You know, it's liquid, it's not a gas like chlorine, you can outrun it. Anyway, this bromine is 79.904 grams per mole. There's 3 of them. And so our total formula mass, that comes out to 239.712. And our total formula mass for antimony bromide is 361.672 grams per mole. Conveniently enough, I already calculated how much 3 bromines cost. So when I want to know, I also, by the way, I don't have a yellow marker, but I have this highlighted. I want to know what percent of this compound is bromine, right? What percent of the total is made up of this element? Because maybe I want to extract the bromine, or maybe I want to know how much bromine I need to make it, whatever. I can do these calculations very simply. So the percent bromine is equal to the mass of the bromine by weight, the percent by weight. It's 1/4 of the atoms in there, since there's 4 atoms total. 0.712, and we've talked about the law, and you were tested over in the last test, the law of conservation of mass. But 239 divided by 361.672. So this divided by that total. And if you do it, that's equal to 66.3%. And that is your answer for the percent bromine. Okay? I said, what if you got percent antimony? If that was your question. Well, what if you did it and you're following me and you wrote down bromine, you say, mine asks for a percent antimony. Now you got to divide this by this to get it. And you can do that, and that's the way you're supposed to do it. But I only have 2 elements in this compound, so if one of them 66.3%, the other one is what? 33.7%. They have to add up to 100%. Law of conservation of mass. Let's go on to the next one. Or let's go down one more with more elements in it. The next one has 2 elements. It's the same process. The next one down is aluminum phosphate. Aluminum is a group 3 metal. If you use the Roman numeral classical numbering system, which I do because I'm old, but it's also more convenient. It's group 3A in the representative elements, and that means it has a +3 charge because it's group 3. And phosphate is one of those polyatomic ions. If you go to the chart, it has a -3. So there's 1 aluminum, 1 phosphate, 1 aluminum atom, 1 phosphate atom, and 4 oxygen atoms. And aluminum is, and it asks for what is the percent phosphate. So, I have this phosphate, and it's in bold, it's thicker, more obvious than the others, and it's highlighted. So I also have it highlighted. Like so. With my highlighting, of course my highlighting was yellow, not orange. And I want to know what's the percent phosphate. Percent phosphate. And it's equal to what? The mass of 1 phosphate and the divided by the mass of the total compound. What percent of that compound, that ionic compound, is made up of phosphorus? So, aluminum is 26.9815 grams per mole. Your mileage may vary. Here it's 26.981538. The one I looked up had 9815. And then we have phosphorus, which is about 32. No, not 32, 31, right? Yeah. It's equal to 30.9738. I only say 31 because, in the lab, I don't write 15.9994 for oxygen and 1.00794 for hydrogen, because when you go out 4 and 5 places, and I'm weighing these compounds out on my top loading balances like we have right here, those don't matter so much. Now I do for making up standard solutions of ACS certified chemicals that I know are pure and dry. Nothing's dry in Arkansas, where it's usually too hot and always too humid. But I have analytical balances that can weigh a fingerprint, basically. We have to use special techniques to weigh things out, and we can weigh out to 1/10 of a milligram, or to the 4th position, 0.0001 gram. But we seldom go that far. Our oxygen has a mass of 15.9994, as we said, but I have 4 of those, so it's equal to approximately 63.9976. We've seen that number several times today. And if you add it all up, the formula mass for aluminum phosphate is 121.9529. And this is one thing some of you may notice. Sometimes I take these compounds and put them on the first page and say, what's the formula and what's the formula weight for aluminum phosphate? And I'll take some of the ones on the first page, like we did ammonium sulfate, and ask you what's the percent sulfate in that compound. Anyway, let me move this down. Our percent phosphate is equal to phosphate's 30.9738 divided by 121.9529, and if I work that out, my percent phosphate is equal to, you can see 131 and 122, it's basically about a fourth of the mass, 25.4%. And that is your answer. Okay? You have two more. There, I worked half of your homework assignment, gave you half the answers, and I hope I showed you the path to get to those answers. And if you have any questions, call or text or send me a message through our LMS, our learning management system, whether it is Canvas or Blackboard or Moodle. And be patient, and it doesn't hurt my feelings if you send me another message or another text when you don't get a message soon enough, but and I'll get back to you and we will get those answered. So these assignments are long, they take time, whether you're looking up answers or calculating them or using the book or using my notes, searching for these answers, whether you have experience doing these problems from high school chemistry, and it's going to get harder and it's going to get more time consuming, but for online and with basically online open book assignments and tests, this is my way of ensuring that you spend the time with your chemistry and studying chemistry, and that you get enough to retain, and if necessary, this is regular majors chemistry, enough to get the basis you need to go on into second semester chemistry. That's it for exercise 3.2. I will see you at the video help session for exercise 3.3. Goodbye now.